Bienvenidos, Ushamadid, and welcome Anne Arundel Community College learners from the CTS-130 Section 402 course for the spring 2021 semester. This is the Cisco Networking Academy Introduction to Networks version 7 course curriculum, and in this supplemental video tutorial on IP assignment number 1, we are now going to turn our attention to converting decimal to hexadecimal. Now, this is typically one of the more difficult conversions for learners to make because of the intermediate step that we need to consider. So let's dive into that same activity that we're looking at, and we're going to be working with questions 16 through 20. So, how do we convert from how do we convert from decimal to hexadecimal? Well, we first need to convert to binary. So that's the intermediate step, is to go from the decimal value of 47 to the binary value for 47. And now you're going to see why I was talking about the high order bits and the low order bits and grouping things into 4 bits, which we refer to as a nibble. So we're going to break the octet that we get, the resulting octet from converting this decimal value into binary. We're going to break it into 2 nibbles, 2 groups of 4 bits each, and then we're going to get the hexadecimal representation from there. So what does that look like? Well, as a review, remember, when we're dealing with our 8-bit positions, if I'm putting the values going from left to right, the high order bits come first. So 128, 64, 32, and 16. These are my high order bits. And then we've got 8, the low order bits, 4, 2, and 1. And based on whether or not the bit position is on or off, that allows me to add up and get my decimal value. Well, when I have the decimal value, we do what we just did in the previous activity, is I say, is 128 less than or equal to 47? If it isn't, the bit position is off. So then I go to the next bit position. Again, I'm going from left to right. So now I look at 64. Is 64 less than or equal to 47? It is not. What about 32? Well, 32 is less than or equal to 47, and that would leave me with 15. Is 16 less than or equal to 15? And again, if I was to draw this out over here and say 47, and if I was to take away 32, you can see that we're left with 15. I'll make sure I put all the steps out here so that you understand. Again, you might be looking at this saying, oh, well, that was easy for me, but there may be other learners who are trying to figure out, well, wait a second, how did he end up with 15 remaining? So if we have 15 left over, I look at the last high order bit position here, or 16, and I say, no, that is not less than or equal to 15. But what about 8? Well, 8 is, and there's that little conspicuous space I'm going to leave here between these 4 bits, this nibble, and then these 4 bits, or that nibble. So 8 is less than or equal to 15, and that's going to leave 7. And so then 4 is less than 7, leaving 3. 2 is less than 3. Subtract 2 from 3, I get 1. And 1 is less than or equal to 1. So here is the division that we end up with the 8 bits. Now, this is the part that kind of trips learners up because we've been working with these decimal values across the top here, right? However, when I'm converting from binary to hexadecimal, I no longer care about these top 4, the high order bit 4 values, because these are now each their own independent, mutually exclusive set of 4 low order bits, meaning for both of these, the rightmost position has a value of 1, and then 2, and then 4, and then 8. And the same is true here. We don't go 16, 32, 64, 128 because now it's its own mutually exclusive, independent 4 bits. It's its own nibble. So 1, 2, 4, and 8 would be the decimal values for each of these bit positions, and it would be the same, right? These guys are the same in terms of the decimal values that correspond to the bit positions because they're their own 4 bits at this point. So now that we took our decimal value of 47, we convert it into binary, and this is the step where learners typically get tripped up. We convert it into binary and then simply draw a line, something to separate the high order 4 bits from the low order 4 bits so that we end up with 2 groups, 2 nibbles, each with 4 bits, and now each of them with the same decimal values for the bit positions. So now all I need to do is convert to hex. Well, remember, with hex, 0 through 9, that's easy, right? Because 0 in decimal would be 0 in hexadecimal, and 9 in decimal would be 9 in hexadecimal. It's when we get to 10, 10, 11, 12, 13, 14, and 15, which is where things can get a little bit tricky. So 10 has a value of A, and sometimes you'll see it as an uppercase A, other times you'll see it as a lowercase a. 11 is B. So these are decimal values on the right-hand side here. So let me actually write this up here. So we'll say these are decimal values, and these are going to be my hex values over here on the left. So 10 in decimal is A in hexadecimal, 11 in decimal is B, 12 is C, 13 is D, 14 is E, and then we reach the highest hexadecimal value for a single hex character that we're dealing with, which is F. So if you saw something that had G, H, I, J, K, and it was asking you, is this a valid hexadecimal value? You could confidently say no, because I know the last hex character for an individual hex character is going to be F, which has a decimal value of 15. So now we come back. So how does this tie in to this binary value that I have here? Well, remember, we now sort of changed the decimal values that correspond to each of the bit positions here in this high order nibble that's now all by itself. So now what we do is we look and we say, okay, we do a binary to decimal conversion again. So which bit position is on in this nibble? Well, it's this one here that corresponds to the decimal value of 2. So 2 in decimal is what in hex? Right, well remember, 0 to 9, they're going to be the same. So 2 in decimal is 2 in hexadecimal. Now we look at this other nibble over here. This is going to be a little different. Every bit is on, meaning 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. I come over here, 15 in decimal is F in hexadecimal. And so with these 4 bits, the single nibble, we end up with a single hexadecimal character. So now let's dive in and let's do another one here. Again, remember, going from decimal to hexadecimal has that intermediate step, and that's typically where the mistake is made. Because we now know it's easy to go from a decimal of 155 to binary. So if I was to convert 155 to binary, we know that the 128-bit position is on. And if we were to have 155, which is what we started with, and 128 is less than or equal to 155, we would then subtract 128 from 155, where we're going to end up with, we're going to borrow from the tens position here. So 15 minus 8 is 7. 2 minus 4 is 2, 1 minus 1 is 0, so we're left with 27. So the 64-bit position, 64 decimal value bit position is off. The 32 decimal value bit position will also be off because 32 is not less than or equal to 27. And then we get to 16, which is less than or equal to 27. So then we end up with 11 as the new value that we're working with. So is 8 less than or equal to 11? It is. And that would leave me with 3. Is 4 less than or equal to 3? No. But 2 is less than or equal to 3, which would leave me with a remainder of 1, and then 1 is less than or equal to 3. So that bit position is on. So now we slice that octet into 2 independent, mutually exclusive 4-bit nibbles, and our values, we reset the values here to what they would be if these were each their own little low order 4-bit nibbles, 1, 2, 4, and 8. And the same is true over here, 1, 2, 4, and 8. And we then go ahead and do our binary to decimal. So 8 plus 1 is 9. And over here, 8 plus 2 is 10. Plus 1 is 11, and we convert now from our decimal values to hexadecimal. 9, we know. 0 through 9 stays the same. But 11, you don't write 11 here. That's a mistake that gets made often. We come over here to our trusty chart, and we see that 11 in decimal converts to B, as in boy. So there's my hexadecimal value. It would be 9 Baker. Now, I'm going to be touching on something here that I don't recommend you do to solve these problems. I recommend you work these things out by hand because maybe you don't always have a trusty calculator. So on the Mac, if you open the calculator application up and you come up to View and change it to Programmer or hit the Clover 3, this is the calculator view that you would get. So let's check. I'm going to show you a way to quickly, I would use this to maybe check your work, but don't use this to solve the problems because that's not going to help you when you're taking your CCNA or you're maybe taking an exam in conditions where you're not allowed to look at the calculator app. So we'll clear it here. Now you'll notice we have 8, 10, and 16 here in this little box, a little rectangle area here. And so base 10, those are the decimal values we're dealing with. That's base 10. So 155, 212, 87, 255. Those are base 10 values. And in order to get the hexadecimal value in the programmer view of the Mac calculator, I would simply enter in with the base 10 highlighted, the decimal value I'm interested in. This first one was 47, and then just click on the hexadecimal, base 16, and that converts it for me immediately. And so I can see 0x, 2f, and I'm going to talk about the 0x here in a second. But then we get 2f. So is my answer here correct? Absolutely, 100%. So let's clear the screen. And actually you could, once you get the answer, you could do it in reverse. So let's come to the base 16 and let's type in 9b. And then we'll hit base 10. 155. So we've reverse engineered, gone from hexadecimal to decimal with our calculator app, and everything looks good. So let's slide the calculator over here for now. Let's clear things, but again, let's do this by hand because this is going to help us in the long run. The calculator may give you the right answers, right? But understanding the process, right? It's not about the result as much as it is the process. That's the important thing, is to get the process down. The result will come. But without the process, and you end up in a situation where you're trying to figure things out and you don't understand the process, I can almost guarantee you're not going to get the right result if you don't have, the calculator handy. All right, so 212, that is our decimal value. Let's convert it into 2 nibbles, 2 groups of 4 bits, but to do that first, we got to convert it into binary. So 128 would be on, and if I quickly was to say over here, 212, and take away 128, because that bit position is going to be on, because 128 is less than or equal to the number we start with, 212. So what do we get? Well, we got a lot of borrowing going on here, so that would end up being a 0. So 12 subtracted from, or 8 subtracted from 12 is going to give me 4. I can't take 2 from 0, but I can take 2 from 10, and that's going to leave me with 84. So the 64-bit position is going to be on. And we can kind of do that in our head, right? That's going to leave me with 20. So 32 is going to be off. 16 is going to be on because the number we're working with now, 20, what we have left, is less than or equal, I'm sorry, the bit position 16 is less than or equal to 20, less than or equal than 20. So 20 minus 16 is going to leave me with 4. Now at this point, I kind of should be able to figure out, okay, if the last values I'm going to be dealing with are 8, 4, 2, and 1, it's going to look like this. 8 is not going to be on. 4 is. That takes me to 0, meaning mission accomplished. Now we split this in to 2 mutually exclusive, independent 4-bit nibbles. And we convert from the binary back to decimal, keeping in mind that these are independent, low-order 1, 2-bit values that we're working with now for both of these. 1, 2, 4, and 8. So what do we get here? 8 plus 4 is 12, and 1 is 13. But that is not a hexadecimal character. And then over here, we end up with 4. So I look at my trusty decimal to hexadecimal chart over here, and I see that 13 is D, as in David, and then 4, right? Remember, 0 through 9 in decimal are the same in hexadecimal. So then I end up with D4. So now I can come to my calculator and say, okay, 212, click on the base 16, 0x-D4, and now the 0x conversation is going to begin when we get down here to 25. So let's take a look at how this is going to break out. So 25, 128, that bit position is not going to be on. 64 is not going to be on. 32 is not going to be on. 16 will, and that leaves me with 9. So if you're kind of crafty in your head, you would be thinking, well, 9 would be 8 and 1 with the 4 and the 2-bit position off, and you would be right. So now when I divide these up and I go to convert from these independent 4-bit nibbles, low-order bit values of 1, 2, 4, and 8, what do we get? Well, over here, we end up with 1, and I'll write it above here. We get 1. Over here, we get 9. And so then there is no decimal to hex conversion I need to do in terms of the letters, right? These values that are 10 or greater. The hexadecimal number is going to be 19. But let me ask you, if I wrote that down and I said, can you tell me conclusively, is that a decimal value or a hexadecimal value? You might be hard-pressed to argue either way, because there's no way for me to know, looking at this answer, whether you mean hexadecimal or decimal. And that is where our friend 0x comes into play. And so, and that, again, I specifically left that out on purpose because what you would want to do when you're writing your hexadecimal values, it's a great habit to get into to precede any hexadecimal value with 0x, because that removes all guessing. That will remove any doubt as to whether or not it is a decimal or a hexadecimal value in cases where it's not abundantly clear. So here, D4, you could probably look at that and say, yeah, that's hexadecimal. 9B, well, there's a B in there, so yeah, that's hexadecimal. 2F, okay, that's hexadecimal. But 19, if you're in the habit of not writing the 0x and you simply write 19, you could be causing a huge problem for yourself. And it could cause a lot of confusion. So the answer to number 19 I'm sorry, it just so happens that the answer to number 19 is not the decimal 19. It is, and let me get rid of that, that's a terrible zero. It's 0x19. Okay? That is the hexadecimal representation that we want. And let's confirm that. Let's come to my calculator. I'll clear the base 16 and let's put in here 19, and you can see 0x19 in base 16, which is hexadecimal, converts to 25 in decimal. But that 0 lowercase x, very, very important. All right, well, let's clear the screen and let's tackle the last of the questions. Now, this is also going to be the easiest one we deal with, and I've removed our hex chart because we're not going to need it. What did we say about 255? What does the decimal 255 convert to when we go to convert it to binary? Well, all bits are on. So this will be an easy one. And there's that conspicuous space between the two, right? The two nibbles, the two 4-bit values here. And now they're their own independent low-order 4-bit nibbles that will have the same 1, 2, 4 low-order values that we're interested in, 1, 2, 4, 8, and then 1, 2, 4, 8. And again, with 255, we should know in the low-order 4 bits, when all of those bits are on, the value is 15. 8 plus 4 plus 2 plus 1 is 15. And then to go from that decimal to hexadecimal is easy because that is the highest hexadecimal value for an individual character that we can have is 15 in decimal, and that's going to convert to F as in foxtrot. And so we get FF, and that's what you will see. And again, FF might be obviously hex, but let's precede it with 0xFF as habit so that we know we are representing a hexadecimal value. All right, well, that is obviously the tougher of the 5 problems here, the tougher of the problems out of these 30 or so problems that we're dealing with. Now we're going to go into address classes in our final video. So hopefully you've got a really good understanding now of how you would convert from a decimal value to a hexadecimal value. Again, it's the intermediate step, that decimal to binary conversion, and then the breaking up of the binary octet into two 4-bit nibbles, and then understanding that they're their own independent 4-bit nibbles, low-order decimal values now that you're going to be converting back into decimal. Then you convert it to hexadecimal. And always precede your hexadecimal representations with 0x. All right, well, thanks so much for watching, and I will see you in our 4th and final video on address classes.